First of all, thanks to the organizers. It's a great pleasure to be here, and I enjoyed it very much. I will sort of continue along the lines of what Daniel already said, but also there's a big connection to many of the earlier talks. Basically, the title could have also been Minimal Models and Applications of Minimal Models, so I'll show you some actual calculations and applications that we do. This is an outline of the presentation. So first part will be, I'll try to do relatively quickly, which is now we've already seen this construction of minimum models. Let me focus on a few other aspects of that, and then go on to try to focus on do these models actually support altermagnetism, and what can we learn from them? I mean, why should we even apply these minimum models? What are their strengths? And then move on to talk about some Landau free energy, because we can derive the Landau parameters. What can we learn from that? And that will be the most part of the talk. Then a little bit optimistically, I hope to have time to also tell you a little bit about local signatures of altermagnetism and superconductivity in the altermagnetic state. The good news is that the next talk is at 4 o'clock, so there should be okay time. All right, these are main collaborators of this project. Will give us some taste of what's in these 4 papers. These people are very important. Massé has been the driver of a lot of these calculations, but is really a great collaboration with Daniel's group. I highlighted these people are all from Copenhagen, students and postdocs, professors, and these three are all here. Andreas is deeply involved in everything I'm going to say. Okay, is moving to Uppsala in a few months. All right, so a few years ago we were very motivated to try and construct these kinds of minimal models for altermagnetism. I mean, clearly we have DFT calculations, and DFT calculations are great, and we need them in many respects, but they are material specific. So it would be nice to have some simpler models to work with that we could also apply to study mechanisms, simple physical properties. Maybe we could derive analytical expressions and see parameter dependencies and so on. That was part of our motivation for this. And so this is the minimal model in the simplest case. There are more extended versions of this, but as you heard several times earlier today, tau is now sublattice space, sigma is spin, and we have our generic dispersion. There's some inter-orbital hopping. This is a very important parameter. This basically, the altermagnetic symmetries comes from this tau z hopping. We have our altermagnetic order parameter and spin-orbit coupling. The tau z and tau y are very important because they transform non-trivially under some point group operations, the ones that swap the active magnetic ions. And as Daniel said, the spectrum of the spin splitting comes from this. Basically, you multiply this out, so you have your altermagnetic order parameter times this tau z. Okay? So the momentum dependence of the spin splitting is completely determined by your point group and the Birkhoff positions of these magnetic ions. Right? So it is a very versatile model, can describe lots and lots of materials. And maybe I will try to focus on that a little bit. So we have used it for orthorhombic, tetragonal, hexagonal, cubic, rhombohedral materials with D-wave, G-wave, I-wave, spin splittings, and so on. But one thing that I think is also worth mentioning is that, of course, this is not to replace DFT calculations, but in conjunction with DFT calculations, we can get models that are semi-realistic even also, okay? So this was a few years ago where we thought that this was the fruit fly, the rutile ruthenium dioxide, but now I don't know if it deserves the name of flattering name of fruit fly anymore, but in any case, it's a good example of a tetragonal system with D-wave symmetry, and you can then, by fitting to some of the DFT bands, actually obtain reasonable models for actual materials. This is a case where it was ruthenium dioxide, and this is some of the bands that are present here. There are other bands that can also be included in this model. Okay? So that's quite nice. And since then, we have also applied this to thrombolic materials. I'll return to this later. Hexagonal cases, Lie lattice materials. This is a more relatively new thing for us. 2D layer groups. I will return to this also in the end of the talk. And as Daniel said in this paper, we've listed many models, as all the models from this centrosymmetric space group with magnetic ions on inversion symmetric Wyckoff positions with multiplicity 2. Okay? And every time you see tables in this talk, it means that Daniel was very deeply involved. I don't really do tables, you do tables, but yes, it's very useful. Go in there, find your model, it's in there. Okay, now let's ask a different question. Do these minimum models actually even support altermagnetism? And in that case, we simply go to the normal state, add the on-site Hubbard U, and we can do a couple of things. One thing is to calculate the associated RPA susceptibility, mu and, these indices are here, sublattice indices, right? And for this example with this band structure, we're focusing on collinear physics, so we have either an ferromagnetic or an altermagnetic susceptibilities, and those can just simply be calculated. And what you see, this is the bare ones, this is the RPA ones, and you see the Q equals 0 altermagnetic susceptibility is clearly winning. That's the peak, and we can go in and test this. Andreas did his self-consistent Hartree-Fock studies, and also this is the altermagnetic susceptibilities for various chemical potentials. Quite generically, it's nicely stabilized. So actually, they do support altermagnetism, but also this is a way to, when self-consistency is important, for example, if you're interested in collective modes and spin waves and itinerant systems and so on, this is a great way of approaching that problem, I think. Yes?
Go. No, my question is, of course you have the ferromagnetism also here. When I look at your table, the ferromagnetism, previous one, your figure, well, I was just looking at the figure that you just showed now. Exactly. Ferromagnetism, it's also there. So you have basically two-phase transitions, or what, as a function of U, or how should I?
This means that, this is a function of U, so the leading one will be the altermagnetic one. Okay, the ferromagnetic is subleading.
It's subleading.
In agreement with the fact that susceptibility is much smaller.
Okay. Thank you.
Yeah, after me.
Did you ever look at the nematic, just the nematic phase, the one that is not going to break the time reversal? Is that a competitor? I would not assume to be the leading instability, but is it a nearby instability? Essentially making the two occupations different, right, of the two sites.
I don't think we looked at that, no.
So in this calculation, can you think of this critical U as a Pomeranchuk instability, essentially? Because if you were to compute the Landau parameters coming from the normal state.
I don't think so, but we can discuss later to what extent that is actually true. But the important part of my talk is that sublattices degrees of freedom are very important here. So,
physics is important.
Okay, no, I understand that, yes.
So in that sense, it's not Pomeranchuk.
Right, but if you are, that depends on where you are in the chemical potential, in a sense.
Yeah, but also the ferromagnetic is Pomeranchuk, but I say altermagnetic is not. It has
in this sense.
band terms, and then the ferromagnetic may.
Okay.
Here's another question.
If you look at the table of your materials, you see some of them are not so really strongly correlated, but they have a lot of hybridization, and therefore I would like to ask you whether you have thought that the interatomic Coulomb interaction could drive the altermagnetic instability.
We were just discussing that yesterday. So we haven't studied it yet, but it's a very interesting question. And actually, that was Raphael's also a question yesterday. So good point, interesting. We could we could easily, relatively easily look into that, I think, yeah. Yeah. Okay, so let me now, okay, so because these are relatively simple models, right? They are 4x4 matrices, so you can also do some analytical calculations, not just do numerics. And actually, if you just compute these susceptibilities, then the difference between them is there's a very simple expression, and this quantity will return again and again in my talk. So there's a competition between intraband terms and interband terms. Okay? So actually, when the interband terms dominate, altermagnetism dominates. Then that susceptibility is the leading one. Okay? So band degeneracies of this form help altermagnetism. So that is interesting and may give some insight into the fact that most altermagnetic, or many altermagnetic materials are existing in these non-symorphic groups where you're guaranteed to have these kinds of band degeneracies at the Brillouin zone edges.
If you would do strong coupling, so go half filling, do T squared over U, Heisenberg, you will not find anything, not find any altermagnetic state, right? It's a frustrated magnet in that case.
I'm not sure about that. I haven't seen anyone actually do that.
You can. But you have your longer range interactions frustrating with your nearest neighbor interactions. So, okay.
Isn't it like Raphael said, that you have to put a cosine in your parallel or something? So you have like some...
I'm just saying, do Hubbard T squared over U and look at the Heisenberg model, and then you will have frustrating interactions. You will not get ferromagnetic interactions out of a one-band Hubbard model anyway. So it will everything will be anti-ferromagnetic, and because you have longer range, it will be frustrating.
Wait, but you have also, I mean, the longer range ones are complicated, right? Then you have many contributions to those that can give you ferromagnetic couplings.
In the single band model it doesn't, but in the multi-band model, sure.
Yeah, very good questions. Okay, so let me now. Okay, so this was the end of step one. This is all in this paper what I've talked about so far. Let me switch gear a little bit and go to the general form of the Landau free energy. This is a rather generic expression, right, for orthorhombic systems or higher symmetric ones, where we have now my altermagnetic order parameter is n, not j anymore, and I have a magnetization, actual magnetization with its capital M. Right? A nice thing about sort of a minimal model approach is that you can really compute all these Landau coefficients. So we've done that. They're all in Mercier's PhD thesis, also for gradient terms and so on. But let me now focus on that particular one in this talk. Okay. So this is a coefficient that is non-zero if we have spin, or it can be non-zero if we have spin-orbit coupling. Okay. Many people have studied spin-orbit coupling. Many people in this room have studied spin-orbit coupling. We know that it also gives us preferred directions for moments. We can have large, when it's allowed, we can have large anomalous Hall effects, associated weak ferromagnetism, and so on. But what I would like to emphasize here is if we compare in the literature from DFT, what are these ferromagnetic moments? It really is hugely dependent on the particular material you look at, and many orders of magnitude differences. So basically vanishingly small for these compounds and rather large for these compounds. Probably you guys know many other candidates that fall into these various categories. So we were wondering, why can that be? Is there some principle for that? And actually, the models that we have, include spin-orbit coupling, quite generically tells you why there's a large, or when there's an allowed anomalous Hall effect, why it's large, because it's linear in spin-orbit coupling. However, the ferromagnetic moments are constrained by quasi-symmetries, particularly in highly symmetric space groups. So that's something I'll try to explain now.
But sorry.
Yeah?
Didn't understand. So that's not true that the ruthenium oxide magnetic, the chromatin, these are pretty large numbers. When you look at the conductivity, no, look at the ruthenium oxide, is non in the when they're on the plane, yeah, they're still large. They're similar order of magnitude as iron. These are still considered large. The conductivity itself is going to be a better hundreds of sims per centimeter. Yes, so that's not considered vanishing. They're still large.
The anomalous Hall effect is large.
Yeah.
Yeah, I agree.
What do you say is vanishing?
No, this is the moment. The magnet.
Oh, I'm so sorry. Sorry.
No, yeah. I think we agree that. So generally it's large. This is okay, sorry. Amazing part of altermagnetism. We have this huge, large anomalous Hall effect, right? Anyway, so it's this aspect. Why magnetization is so orders of magnitude difference. All right, so let's go to our free energy. Again, this is our simple form, and I'm interested in this particular coupling, bilinear coupling. And we know how these different components transform. Yes?
But in manganese telluride and carbonatimonide, you don't have that coupling. You need to go to the cubic term to get that order, right?
Yeah, that'll be part of
okay.
that'll.
But that's not the reason why it's small. Okay.
Well, it's combined. Yeah.
Okay.
Yeah. You'll see in a few slides about that. Yeah. All right. So we have learned from several works, but like if there's a bilinear coupling, we have to have a trivial irrep in this product. So this is the spins, and this is the spatial part. This is a D wave, G wave, I wave symmetry. And they can take an example. D4H is our fruit fly, right? And we have D wave spin splitting. This Pauli matrices transform in this way. And then we're looking for a trivial structure, a trivial representation in this product. In this particular case, since I have the D wave, my altermagnetic order parameter transforms like this, Pauli matrices transform like this. You can easily convince yourself for all the K's to square out. There are these two, or this is the allowed bilinear that exists in this particular example. Okay, and then we can make one of Daniel's nice tables and go through all these different point groups and all the different kinds of allowed possibilities for spin splittings, and you can construct all these bilinears, and you see there are no bilinear couplings down here. That's what you were after, and some of them you do have this kind of bilinear coupling. But there's still a remaining question: is when is this really relevant, and when is it more or less relevant? Okay. That was what we were interested in. So we can get some help from that in our minimal models calculation, because there we have a very simple Hamiltonian. We have the normal state. We treat these two as our perturbation, and then we can just compute the free energy, right? So we go to that, and we go to second order here, and this is the expression that you get. Again, this kind of ratio or combination of these susceptibilities enter. But what you really should see is that the antisymmetric combinations of N and M are the ones that are generated to linear order in the spin-orbit coupling here. Okay, so we can make another column to our table and make a little check whenever this is allowed. And you see that in these D2H, it's always allowed. It's a little tricky in D4H and D6H, because sometimes it's allowed if you have a right spin splitting structure, but otherwise it's not there. Okay. So, and then you can wonder about the other ones, and we have a whole story about the relevance of secondary order parameters, and we can show that in these cases it's quadratic or higher order in spin-orbit coupling. So let's go check. We take some examples. Again, we have the rutile case and we have iron antimony. They are supposed to have very different orders of magnitudes of induced ferromagnetic moments if our tables are correct. But we can just compute it, right? Because we have the model. We can just actually evaluate this product for all the states and sum it up. And you see that for the rutile case, the moment is absolutely tiny. And whereas this is a relevant case for this orthorhombic structure, it's very sizable. Okay, so it actually agrees quite nicely with this general symmetry analysis. We can also look at the anomalous Hall effect, and that was something Massé did a long time. I'll skip how we calculate it, but it's again with these projector methods that Jørgen was also focusing on, and all the details are in these papers. And then this is a nice thing about you can actually get analytic expressions for the Berry curvature, and you can evaluate the anomalous Hall effect. And the main point is that it's generally linear for small spin-orbit couplings. In this case, for the root-tile structure, there are hardly any induced magnetization, so the anomalous Hall doesn't really change whether you include that or not. But we can include it. We can include the M in our calculations of the Berry curvature. And of course, over here, where there is a sizable induced case, that there are some corrections to the anomalous Hall, but it's not important over here. Yes?
I completely agree with what you're saying about being linear or not. But if I just look at the magnitudes, right? I mean, on the left one, you have a 10 to the minus 7. On the right one, you have a 10 to the minus 2.
Here, up here.
So isn't that why one is much smaller than the other?
Yeah.
But how do I see these prefactors coming from being linear or non-linear in the alpha spin orbit coupling?
I mean, here you have directly the linear term, right? So this is a calculation where the Niel vector is in some direction along direction L. Then that spin orbit coupling in that same direction immediately generates these terms to linear order in that spin orbit coupling. This expression does not include the magnetization. It does not include spin orbit couplings in other directions. That's in the supplementary of our paper. There are many, many, many terms to this general.
No, but I'm talking about the magnetization, not the whole. Like I mean, still there's a 5 orders of magnitude difference, and is it really just because one is quadratic and the other is linear?
No, it's because this one is allowed to first order in spin orbit coupling. So this will be large. So if you have some a Niel vector, it will induce a large magnetization. This one is at least second order in spin orbit coupling. So it's tiny.
Yeah, that's the point. Alpha is not small.
Alpha is.
Maybe I
Sorry.
Yeah.
Sorry. Okay. So this is for different spin orbit couplings. Okay. So alpha, this equal to 1 is the DFT extracted spin orbit coupling. Sorry. I should have.
Alpha is still small compared to the kinetic.
I think that was also your. Sorry.
Okay.
I should have explained that better. Yeah.
essentially the same question. What's in the denominator? Yeah. No. I mean, lambda divided by what? Mu divided in mu. In units of mu Bohr is lambda divided by what linear square?
I am being very cavalier about what's large and what's small, right? So large here just means linear and spin orbit coupling. That's what I mean by large.
Statement and then I think I'm done.
What I can say is that this value, alpha equal to 1, is the value of spin orbit coupling extracted from DFT. What exactly those numbers are, I don't remember, but yeah, we can look up. Okay. All right. So comparing then these materials with that we found in the literature, it makes sense that these compounds have a large magnetization because they belong up here, also for iron and antimony, whereas this one I don't know if it's altermagnetic or not, sometimes maybe, sometimes not, but it should be very small. These should also be very small, they're even down here. So I think that's reasonable. Of course, one can ask, to what extent is this general? Okay, is it something that, because my checks and crosses came from minimal models, and for that we have constructed these general arguments based on this quasi-symmetry. How much time do I have?
5 minutes.
In total?
From the 30 minutes.
Okay. Maybe I will just say then that, the quasi-symmetry is a way to, normally symmetry is saying whether something is allowed or not, yes or no questions. Quasi-symmetries can tell you something about whether a perturbation is a large or a small effect. Okay? So the way I've learned it from is from this paper or through discussion with Daniel and Andreas and so on, where you have some accidental degeneracies and you see what happens to these band degeneracies as you put on some shear strain. And through the quasi-symmetries, so these are symmetries that are valid for the unperturbed Hamiltonian, you can understand what couplings are allowed and couplings are not allowed. Okay? So if they're allowed, they will give a large splitting. If they're not allowed to linear order, you have to go to higher order. For example, in this case, your orbitals have to mix with other orbitals under strain, and then they couple, so it's a second order effect, and this gives a very small splitting. Okay? So this is the thing. So for our minimal model Hamiltonians, let me try and do this a little bit quickly. We have the full symmetry of the full Hamiltonian. Or this is without spin-orbit coupling at all. This is with spin-orbit coupling. But now we consider a Hamiltonian where we only include some components of the spin-orbit coupling. Okay? So we have some kind of uniaxial symmetries around the axis of that particular component that spin-orbit coupling has. Okay? And then you can go through the arguments and see what are the quasi-symmetries. And the point is that in this example, for a tetragonal case, this antisymmetric product is actually really what's allowed. It's even under that quasi-symmetry, so it should be induced to linear order in spin-orbit coupling. Okay? So it's a general result. It doesn't just rely on our minimal models cases, but it really you can tie these checks and crosses in our tables with the presence of such quasi-symmetries or not. Okay, let me very briefly then go to the last parts. So this is a project of altermagnetism, and Yannick is here. He has a poster on this. We're looking at 2D models. In this paper, we have sort of characterized all these 2D layer groups and focusing on D-wave example, for example. By the way, here I point out that there's actually a case here with an altermagnet with zero splitting. That's this type 4 case. But the point of this result is that by a non-magnetic or by simple impurity, it doesn't have to be magnetic, you can actually see the spin splitting directly in real space. Okay? So Yannick can explain that all on his poster. There's an important thing here is that this part you would never get starting from a one-band model. Okay? So if you start from a simple one-band model, this kind of a symmetry only exists in the spin channels. Okay? Because it doesn't know about the sublattice structure. Okay? So it's really a case I know of where it's very, very important to start from minimal models that have sublattice knowledge. It makes sense because you're putting an impurity on a particular site, an A or an B site, right? And they're different. Okay, and then the very last part, I will talk a little bit about superconductivity. This is this is a project. It's led by Matt, who's also here, and Christian, who did most of the calculations. It's again a 2D models. We start from the minimal model construction, and there's also a poster on this, by the way, for tomorrow. So the philosophy here is you have your minimal model. We add on-site attractions. Later I will talk about other versions, but let's take the simplest one first. Then we go to band space. Okay, so we have our sublattice space. We go to band space. We know exactly the form of this unitary transformation. It's very simple because it's just 2x2 matrices. And then we can construct the new interaction in band space. And the important part is it inherits this momentum dependence from this transformation. Okay, so so here's the gap structure. You see there is the momentum dependence of these matrix elements. So if you can stabilize S-wave singlet superconductivity, it's hard to do in an altermagnet, but there's a regime of how big is the splitting compared to other things and so on. Then there should be very strong momentum dependence, especially if your Fermi surface crashes into the edges of the Brillouin zone. I think that's related to what you had too. So even an S-wave superconductor has very strong momentum dependence in the altermagnet, depending on the Fermi surface. If you're in the middle of the Brillouin zone, the one-band calculation can be very good. Okay, we've also there's this kind of blocking effect, and the blocking effect is simply that if you're on the edge, you cannot pair an electron on A sublattice site with spin up on an electron on the same sublattice with spin down, because the sublattice weights exactly block this right there. Okay, so that's an interesting effect. It's actually also there for normal antiferromagnets, but maybe it's more relevant for altermagnets. We also looked at nearest neighbor couplings, and we found some interesting D-wave factors. But then we put it on the archive, and Marcel was asking, hey, what's happening here? I mean, we have this kind of Fermi surface, right? And so you should really expect that this, if you're looking at Q equals 0 pairing, you should have a pairing triplet, equal spin triplet pairing, right? You want to pair blue with blue, red with red, and blue with blue. So that's the expected leading channel. However, for nearest neighbor pairing here, you have the same sublattice, right? This is sublattice weight, right? So you have the same sublattice weight if you go from K to minus K. And you're trying to pair states on opposite sublattices. So that's another kind of blocking effect that exists in the pairing channel. Then you suggested you should go to, I don't know if you forgot, maybe you forgot, but let's try to go to next nearest neighbor pairing, because there you should really not have this kind of blocking effect. And so we did those calculations, and there indeed we find these 4 degenerate states that has been several is related to what you talked about. There's other papers, I think you will talk about it, maybe Annika, or many people will talk about, has been talking about this. So there are these interesting equal spin triplet pairing states arising here. But in this model, they exist only at longer range bonds, which are maybe weaker, I don't know. Okay. I will finish. This is the conclusions, some application of minimal models. The last parts with impurity, local signatures, and superconductivity. There are posters on this also. Thank you for your attention.
Time for more questions.
Did I understand the last part correctly, that you're looking at superconductivity in the altermagnetically ordered state? So there is an old story that, at least this is in the case of no spin orbit interaction or weak spin orbit interaction, that the coupling to the spin waves is suppressed in the ordered state just because it's a gradient coupling. Shouldn't this play a role here, that it actually in the ordered states the system is not a particularly efficient pairing source, the coupling to spin waves?
I mean, so you're talking about something I can't answer because you're talking about mechanisms, right? And I haven't used a spin fluctuation mechanism. I have to say I am in my altermagnetic state. I'm assuming it's a metallic state, so I'm looking at some Fermi surface. They have this kind of spin splitting, and then I'm assuming there's some attraction.
Right.
I looked at on-site, nearest neighbor, and so on. I mean, we can go back to cuprates, for example. There you also have coexistence regions, right? And there are vertex corrections that kill contribution from spin waves. That's what you mean. Yeah. Right. Mm-hmm. I mean, I think actually in that problem we solved in the cuprates, I think you probably did too. But if you do this properly, these exactly cancel. They exactly cancel that problem.
Yeah. Okay.
So Brian, in the last thing you showed about these 4 degenerate states, right? So one thing that Eduardo mentioned his talk and bothered us for a little bit, and it actually still bothers me, is that there was nothing in the model that chooses between P plus IP up. Like, as you said, there are 4 signs there and they can be whatever, right?
Yeah. Somebody wrote, I don't know who wrote this, but it's kind of similar. Oh, that was you, okay.
But so it bothered, because I don't understand this exodegeneracy, to be completely honest, because I felt that the model shouldn't have this exodegeneracy. Do you understand? Is this something that, I mean, I know that Marcel mentioned if a breaking version, then you lift it, I agree. But do you understand what's the origin of this degeneracy?
I mean, the way, to be honest, we got this picture yesterday from the student, so, but we were discussing. But the way I could think about it is that, let's say you're deep in the limit where you have a huge spin splitting, okay? Then you have basically a spin-up Fermi surface, and you have a spin-down Fermi surface, right?
No,
and the spin-up Fermi surface will do your up, and why should it not do P plus IP? It fully gaps it, right? And
I agree with this argument. The problem is that even after we include the couplings between the bands, this doesn't seem to lift this degeneracy. That's the thing that bothers. I agree completely with your argument, but I couldn't find any way of lifting this degeneracy, or we couldn't find any way to lift this degeneracy.
Okay, maybe you have some insight on this, but yeah. Okay. We can check whether we agree. Yeah.